In this video, we're going to take a look at some of the zero-day research done by Stephen Fewer at Rapid7 into multifunction printers by Brother Industries. So this research came out towards the end of June. I missed it, but I recently went through the white paper and I thought there was some really cool vulnerabilities in here, so just thought I'd make a video to review them. So what we're going to be looking at are the 8 vulnerabilities or 8 CVEs that were registered against 689 models of the printers, scanners and label makers made by Brother Industries. There were also 46 models from some other vendors which were affected by some or all of the vulnerabilities. So total, nearly 750 models across 5 vendors were affected, and it took 1 year from the disclosure to the remediation and the coordinated disclosure. And we'll go through each of the vulnerabilities in detail, but the most serious is an authentication bypass, where an attacker can leak the serial to the printer through several means, including remotely, and then generate the default password from that serial. So it means if the password hasn't been changed, they can log in remotely to the printer. And the worst part of this is the vendor said that it couldn't be remediated by a firmware update because the password is set using some software during the manufacturing process rather than actually any code inside the printer. So that essentially means only the newly manufactured printers are going to be secured against this attack, and the organizations with older printers will need to go and change that default password. Okay, moving over from the blog post, we also have the Git repo here, which has code for each of the exploits on it, and a summary table showing 8 vulnerabilities that were disclosed. There's also the white paper, so in the video we'll just swap between sort of the code, the Git repo, the blog post, and the white paper. Alright, so quick summary, what are the 8 vulnerabilities we disclosed? Well, we mentioned that there's one to leak sensitive information. That's how the attacker can retrieve the serial number, so we'll look at that first. The second and the most severe was the possibility for an unauthenticated attacker to generate the administrator password if they have that serial number. And then, once the attacker's authenticated, there is a buffer overflow, which can trigger a crash. There is an SSRF, which is limited, but that can be used to scan TCP ports internally. There's another SSRF, which can be combined with request smuggling in order to perform arbitrary requests to the internal network. And there are 2 denial of service. One was a logic bug, and the other was type confusion, if I remember correctly. We'll look at those shortly as well. And then the final one is once you're authenticated, it's possible to disclose the password through LDAP and maybe some other services as well. Okay, just before we go into the first vulnerability, here's the testing setup. So they put a diagram here in the white paper, and if you're interested in the exact model and a firmware version and things that were used, you can check the paper for that as well. But essentially, 2 scenarios were explored. One was an internal attack, so the attacker's present on the internal network, and the second is remote, so the attacker is completely external and needs to get access remotely. They also mentioned that they used Shodan in May and found nearly 6,000 Brother printer devices that were exposed to the public internet. So obviously, if you can generate that password and connect remotely to the printer, there's going to be some big problems. So the first vulnerability is very simple. This is an unauthenticated information leak, and essentially, an attacker can make a request to /etc/mount_info.csv on one of 3 exposed ports, either HTTP, HTTPS, or IPP. If the service is exposed to an external network via port forwarding, that can also leak the internal IP to the attacker as well. This will essentially return the node, the model, the location, the contact, the IP, the firmware version, most importantly, the serial number, because that's what can be used to generate the password for the Auth bypass that we'll look at next. So let's take a look at the exploit code for this. It's written in Ruby. I'm assuming this is supposed to be a Metasploit module, although I didn't see it in Metasploit yet, so maybe it's not been added, or I'm using a really old version or something, I'm not too sure. But yeah, quite a simple script. It is taking in some options. We've got some default ones here, so this is the default path. It's going to do HTTP on port 80, but of course that could be changed to IPP or HTTPS. Or if the mount info path has been changed from a non-default, you can specify that as well. But as long as you specify the printer IP, that's all that's needed to run this exploit. And yeah, it'll generate the URI, so it needs to make the request to whatever port was provided, and it will return the CSV file containing all of the sensitive information, most importantly the serial number. So yeah, that's basically it. It makes a HTTP request to an endpoint, it gets back some sensitive data, and then it's going to print that out in a nice format to us. Okay, so the second and most severe vulnerability is this authentication bypass, and essentially the devices use an 8-character password a default password of 8 characters, and it's generated using a custom algorithm which is derived from the serial number. So if an attacker can leak that serial number, and we've just seen that it's very, very easy to do that, then they can generate the default password for the device. So as long as that's not been changed, which as we know, lots of people don't change their passwords, then it should be possible to log in and do a lot of crazy things with the printer and also enable the vulnerabilities that we're going to explore after this one. So yeah, you can use the CV that we just looked at to leak that, or you could also use SNMP as well to walk through that and get back the serial number. And what actually happens with the password generation then? So the exploit is going to recreate this, and we'll take a look at that in a second, but it mixes the serial number with a salt value, which comes from a large table of static strings. That value is then SHA-256 hashed. The hash is base64 encoded, and then the first 8 characters are taken as a default password, which seems pretty weird. Subsequently, the algorithm also substitutes some of those alpha characters with symbol characters. Again, not really too sure why they would do that. It's just kind of security through obscurity, as they say. So here is the code. This is taken from the exploit by the looks of it, but we'll go and take a look at that properly in VS Code because it'll look a bit nicer. And here's the exploitation. Yeah, so to give you an example, you can just pass in the printer IP, the port, and it's going to first try and leak the serial number. So if you didn't use the first exploit already, it will try and do that for you, and then it'll generate the default password. And you can also try and validate that password as well. So it can also try to log in. And it also mentions that if you already know the serial number, so maybe you did the SNMP or the PJL query, you can just generate the password without any network interaction. They confirm this just by checking the serial number that's on the back of an actual printer, and it matches the password that's derived from that algorithm. Okay, so let's take a look at the exploit code in VS Code. The only thing is, I don't really use Ruby too much, and normally whenever I use VS Code, I can go and just like hold down Control and then left click on a function, and it'll like jump to that, but I don't seem to be able to do that apart from, yeah, I can do that with some of these. I'm not too sure what there's something wrong with like the autocomplete. If anybody uses Ruby in VS Code, let me know what I need to install or change to fix this, or if it's possible. But anyway, here's our exploit. Again, I'm starting from the bottom because this is where the main function is called. This is where our options are set up, and you can see the default options. You can see the options that you can provide and what do we need to provide as a minimum. So you need either an IP or a serial number, and then you can also specify if you want to validate the password, and that's it. Yeah, it's gonna go right to the top, I believe. So here's our lookup table as well. So we saw that already. It has like a hard-coded lookup table with these values and salts in it, which is gonna mix up with the serial number. And here's the main function. So if it takes a serial number, unless it's taken a serial number. So if it's taken an IP address, it's going to do this. It's going to get serial number first. Again, I wish I could just, I can click that, okay. But it's opened in a new window. I didn't really want that, alright. So yeah, that's going to just do what we saw in a previous exploit anyway, or the first exploit. It's just going to make that request to the IP on that CSV endpoint and get back the serial. Otherwise, we could have just provided the serial number here as well. So that's it. One way or another, it's got the serial number, and the next thing it's going to do is generate the default password, which is just below that. So what happens here is it takes the serial, which is 16 bytes, and then it's going to append 8 bytes from the salt lookup table that we saw at the top. And those 8 bytes which are appended, it'll also subtract 1 from each of those as well. So yeah, it's applying a few transitions to the data to try and obfuscate what's going on, but essentially this is just a combination of the leaked serial number and some of the hard-coded salt data. Then it is SHA-256, so we end up with a SHA-256 hash, and it's base64 encoded, and then for whatever reason, it's truncated to 8 characters. Well, I suppose we don't want the password to be too long, so I guess that kind of makes a bit of sense. And then it will change some of the characters, so it's replacing any of these characters that it sees with these special characters as well. So yeah, I guess it's obfuscating a little bit, but as long as you have access to the code that was used to generate the password, it's not too hard to reverse this and say, okay, well, we just need to look for each of these special characters and then replace them with the alpha character that it started with, and then we just need to reverse this, so take these salt parts out of it and get back to our original serial number, etc. Yeah, so quite easy for that to be reversed, and There is also the validate password. So that's it. We've already generated the password. That's returned. And if the validate password option was set, which it might be by default, I'm not too sure, then it will also try to log into the printer and just make sure that it works. So you can basically run this exploit and you'll know whether the user has changed the default password on the printer, because if they haven't, you'll get a login. Okay, so we've got through the info leak and the authentication bypass. I mean, I thought those two vulnerabilities were pretty crazy, especially how simple they are, right? The first one is just literally make a request to an endpoint and get the data, and then the second one is deriving the key from quite a simple algorithm and generating the password. Now, once we've got authenticated to the printer, there are some more vulnerabilities which have been discovered. The first is a stack-based buffer overflow, and you can see here, so whenever they were analysing the firmware, there was no symbol info, so they had to rename these functions based on what they thought made sense. It was also an unknown CPU using 32-bit ARM instruction set with thumb mode. The HTTP, HTTPS, and IPP services are on top of an embedded web server called Debut, where every registered URI endpoint is dispatched by a common function shown below. So I was going to try and copy this over into VS Code, but the formatting wasn't too good. So let's just go through the article anyway. We have this common function, and it has this call here, decode params. And it says before the endpoint is processed, it's going to call decode params, which will decode the form or query parameters from the HTTP request. And part of this is also to verify the CSRF token supplied with the request. And we can see here that CSRF token is passed to this other function, decode CSRF token, which will base64 decode the token and then verify it against some expected values. As long as it's valid, it's then going to process some other headers, so the referrer, the host, and the origin, to make sure that it's all matching what it expects, and this is where the overflow is. So let's have a look at the decode CSRF token. A lot of variable declarations there. I think we're going to have something highlighted, which, okay, down here. So there's a lot of code to go through there, but here is our buffer overflow, and you can already see that it is copying a 2048 byte buffer into a 64-byte buffer. So we've got a clear buffer overflow there, and let's see exactly how we can trigger it. So if the CSRF token is in the request, it's going to check the referrer URI path against that to make sure it matches. So it's just mentioning there that it's not actually checking the host, it's only checking the path against the CSRF token. And as long as that succeeds, it will then check the host header against the origin header. But if the origin header is not present, so if we don't supply that in the HTTP request, it'll instead use the referrer header. And it's only using the host portion of the referrer header. So here's the example here. And this is where the vulnerability is. So as long as we can provide a request that has a valid CSRF token, and it doesn't have the origin header, then it means we can put in the referrer header a buffer overflow in this host path. And yeah, I mean, it's a 2048 buffer, so we can provide 2048 bytes here and overflow that 64-byte buffer. I don't think I've missed anything. This is just going to go through the buffer overflow examples, so they're just showing here. In fact, we'll go through this in the script anyway. I think it'll make a little bit more sense. The other thing to mention is that, yeah, we need a valid CSRF token, so you'll need to log in and then first get a CSRF token, which you can do that by making a request to various endpoints, I believe. Did they put one here? Yeah, here's one of them, /boc/boc.html. So once you're logged in, first make a request to an endpoint like this to get a CSRF token, and then it'll be possible to do the buffer overflow. And the only other thing I think to mention, here's an example of that going through. You can see what it looks like in the request. Yeah, the only other thing to mention I think is it's just a crash. There's no like shellcode execution or ROP to like return to libc or get some code execution or something like that. That might be possible, but I think there wasn't enough time to focus on that, or it wasn't worth the resources. So let's go and take a look at the exploit code for this one. Okay, this is probably going to be one of the more complicated to review, but let's just start as we did with the previous. We've got our main function being called down here. It takes in some options, and you need to provide a printer IP, because obviously we're actually exploiting a buffer overflow here. It's nothing that can just be done with a serial number and no access. And you also need the password. So you need to get the password from the first stages that we've already seen. And then you might need to update some of these as well if like the printer, if the company or whatever has changed some of the paths or some of the IPs or whatever, then you might want to update those. Anyway, that's it. Let's go and take a look at the main function at the top. So main, first it's going to get the auth cookie, which is just going to make a request to that /boc/boc.html that we saw. Oh no, sorry, that's getting the CRLF. This is literally just logging in. So it's taking our not username, it's just taking a password and it's going to log in with that password and it's going to return the auth cookie. So that's it, just simple login request. It brings back the auth cookie, and then the next part is going to be getting a SSRF token, and that is the part which I wish I could jump through this a little bit easier with VS Code, but yeah, that's this part where it's going to make the request to that /boc endpoint that we just saw. It's going to extract the SSRF token and it's going to return that. So, alright, all pretty simple so far. Next is the buffer overflow then. This is the post SSRF token. So let's scroll down, and very kindly Stephen has left in some output from the decompiler here so we can actually see what the buffer overflow is doing. And yeah, we know we need to fill up the stack, so here's our variables. We've got 64 byte, as you can see here. We've got a 32, 32, and 32. So we're just starting off with some padding, which is just going to get past all of these variables on the stack. And then after that, we have some more padding. So there is 52 bytes here, which 52 bytes unknown, and then some alignment before the saved registers. And then we have 9 registers that are just being overflowed as well, just with some padding, which is R4 to R12. And then we have the program counter, is just getting A's. And then the X's times 32, this is going to overflow into the previous frame, which is what is actually causing the crash. So yeah, that's the buffer overflow put together. That's going to be put into the SSRF token. And where is it actually being put in? Right here. Okay, so here's our request being put together. We've got a body, we've got our headers, and then yeah, here's our buffer overflow in the host portion of it. So yeah, I think that's that vulnerability. It'll be interesting to see if anybody does maybe make a shellcode exploit for that, or some like ROP if it's possible. I'm not too sure what the binary protections were on a printer, although I doubt it has everything disabled, but pretty cool vulnerability anyway. Next up, we have the first server-side request forgery. So this requires authentication, and basically there is a web services feature on port 80 which takes an XML-based SOAP request, and it allows a client to perform printing and scanning operations on the device. And it mentions that one of the schemas available for this is WS addressing, which allows a request to define where a message's reply or fault should be sent to. So you can put in these elements, reply to or fault to, and they can contain an address element which defines the URI of a remote endpoint that should be used as a destination. So it gives an example here of a SOAP request that will call the scanner's getActiveJobs request operation, and here's the XML format. So we've got the reply to, and then the address is being set as a local address on the network. So this is a random path on some other port on the same IP. And the SOAP request, the target device, can be made with the following request. So here's a request they make, they send that XML. The funny thing here is the device responds to the client that made the curl request below. So let's have a look at the request below. So it actually responds with the post request and all of that output rather than sending it to the internal host. If they open TCP port 4444 here, they'll see it establishes the connection, but it doesn't actually send any data. And this basically means that an attacker can loop through all of the ports and IPs on the internal network to try and see which ones will accept a TCP connection. So it's like a limited SSRF which allows some internal port scanning. If the port is not open, it will respond with a bad request, whereas if the port is open, it will return. Actually, let me just double check what the port open was. Yeah, it just comes back with a 202 accepted. And that allows you to build a TCP port scan capability. Alright, cool, let's go and take a look at the code. Okay, here we are, and I'm trying to get through this a little bit more quickly now because I'm realizing how long the video is going to be. This one doesn't have a main function, it's set up slightly differently to the previous ones. We have our options up here, and it will take the printer IP, and let me see the defaults actually. Yeah, okay, so by default this is going to do all ports. It'll scan all ports on the IP that's provided. You can specify your own if you only want to do a certain port. Oh, this is the scan port. If you only want to scan certain ports, you can do that here. If you want to scan a certain IP, you can do that here. But we need, obviously, the external IP and port, and it's going to take in the ports that we provide, or it'll do all ports, and it's basically going to call this scan port function, which is up here. So it takes an IP, it takes in a port, it generates that XML, and it just replaces the IP and the port with the ones that we want to probe. And then it's going to make that request, and it will return the response, and based on the response we'll know is the port open or closed. And that's it. It's just going to print out if the port is open, otherwise it won't print anything, and if there is an internal IP leak then it will also print that as well. On to the second server-side request forgery. So there's a feature of the web service which allows a client to subscribe to events and receive notifications via a web services event in schema. It's vulnerable to SSRF, but unlike the previous one, this one does allow for data from the device to be sent to a registered URI. There is also a CRLF injection, carriage return line feed injection, that can be leveraged to perform HTTP request smuggling, so an attacker will be able to perform arbitrary HTTP requests to an address of their choosing. However, the response is not transmitted back to the attacker, so this is known as a blind server-side request forgery vulnerability. And here's a diagram showing how the attack works. So firstly, an attacker will issue a subscribe operation with the victim's URI to receive the notifications. Secondly, the device will respond with subscribe response containing the UUID, and that can be used later to unsubscribe as well. 3. The attacker will trigger a subscription event by performing a WS print job request operation, which will trigger the notification to the URI from step 1. Step 4, the device will send a post request to the URI, but due to that CRLF injection, an attacker can perform request smuggling here, so they can send any method, any path, any query, any headers, any body they want. Step 5, the attacker will receive a WS create print job response from the device with a print job ID. Step 6, the attacker can issue a WS eventing unsubscribe operation to avoid duplicate subscription notifications. That's what we mentioned there in part 2 that they can do from the UUID they get. And then 7, the attacker can issue WS print cancel print job request operation to cancel the print job from step 3. So first you need to set up the subscription to get the notifications with the victim's URI. You need to get the UUID so that you can later cancel the subscription, and yeah, you'll do your request smuggling with a CRLF injection and just clean everything up afterwards by cancelling the print job and unsubscribing, and that'll prevent any duplicate subscription notifications. So part of the subscribe SOAP request looks like this, and you can see the CRLFs in there, the %0D, %0A, which need to be HTML encoded, so they're put into HTML entities, and this will force the WS eventing notification to send the decoded characters as part of the raw HTTP stream. So this allows for HTTP headers to be added to the stream basically, which in turn allows for the HTTP request smuggling. Also to mention, to smuggle a new HTTP request, the connection must first be forced into keep alive mode so that multiple requests can reuse the same TCP stream. The first request is truncated by setting the content length to 0, which allows the attacker to inject the second request into the stream. The second request is fully attacker controlled, so it has the method, path, query, header, and body that the attacker wants. And then finally the connection is closed with connection close, and that will ensure that any trailing data is dropped. This one is more of a straight up POC. I don't see like a set options or a main function or anything even. It just has these two requests which it's going to smuggle. And these are just set up as examples, right? So they both go into the HACS endpoint on the same IP and port, but they'll have different get parameters, and they'll also have a different body as well. And these are the requests that are going to be smuggled. So it's quite hard for me to work with this in VS Code. I don't like that whenever I whenever I do control and left click, it opens this as a new window instead of just jumping up to the top. So yeah, let's just speed through this one. So it's basically gonna perform the request. It takes in all those parameters that we just saw for the request we want to smuggle. It's gonna make the addresses. So let's go down here. This is where it is actually building up the request. You can see it's doing the CRLF injection here as well, and the keep alive that's needed. And yeah, that's it building the request. Let's see what was next. It is do subscribe. So do subscribe is going to build the XML request, and it is also going to have the SSRF address where we want to smuggle our request to, and then it's going to do that request. Basically, it's going to make that request. So you can see the function above is being called. And what is after that is create the print job. So it'll create the print job, which has a job ID in it. Oh, that just goes by the UUID as well, by the looks of it. Oh, here's the job ID. Okay, yeah, so it takes a job ID, and then was that the final thing? Is do unsubscribe? Create print job, unsubscribe, and then cancel print job. Okay. So the next CVE is a simple denial of service, and it says here an unauthenticated attacker who can connect to 9100 can issue a printer job language command that will crash the target device. It'll cause the device to reboot, after which they can just keep repeating that command. And how does the exploit work? Well, there is a print job language variable called formlines, which is meant to be a number value. However, if you set it to something that's not a number value, it'll crash. So you just set it here to a letter instead. And basically a type confusion, right? It's expecting a number, we provide it something that's not a number, it gets confused and it crashes. Okay, nice and simple, and here is the code for this one. So yeah, it's going to be port 9100 by default, and you can specify a delay. Is this the delay? Maybe that's going to repeat it then. Let's see. Takes the IP, it's targeting the printer, it's going to send that letter A instead of a number, and yeah, it's looping, so it's going to keep looping through that, and yeah, here's the delay. So you basically say, alright, I want to try and crash the printer every 10 seconds, or every minute, or every 10 minutes, or however malicious you're feeling, I guess. And we have another denial of service. This one is more of like a logic bug, so there is, well, we already know that there's the web services feature that takes the XML-based SOAP request. We've already seen that with some other vulnerabilities. It also has a retrieve image request element in the XML schema, which contains a job token element, and that's expected to be supplied after a user issues the create scan job request. However, if there is no create scan job request and the retrieve image request is sent with a job token element, it'll crash the device. So basically a logic bug. Here's an example request that's going to crash the device, and you can see here the job token, and here's an example of the exploit running. So let's go and take a look at it. Okay, another simple one. It will take the printer IP that needs to be specified. You don't need any authentication, and it's going to generate this XML document, which, as you can see, has this retrieve image request with a job token inside it. And if that is called without first sending the create scan job request, then it'll crash the device. And that's obviously not being sent here. Again, there is a delay option, which is defaulted to 10 seconds. So it will try to crash the printer every 10 seconds. So it'll reboot, it'll crash, it'll reboot, it'll crash. And that's it. We made it through all of the CVEs that have an exploit associated with them. There is this final one, which is a Passback Attack, and essentially the device supports external service integration, which could be LDAP or FTP, SFTP, SharePoint, whatever, and it'll store credentials for authentication. So if you get access, you can configure the IP address of the external service, and the stored credentials are not cleared. So what that basically means is an attacker can auth to the device using the vulnerabilities we've already seen, leaking the serial number, generating a password, and then they can change the external service's IP to one they control. The device will then automatically attempt to authenticate against it and disclose the stored credentials. This was tested against the LDAP server and FTP server, but I think they believe that it can probably work on other services as well. And does it have an example? Yeah, so here's the panel. Basically, you can just go here and put in the IP address of your choice, and it's going to make a connection to that IP address, and that connection is going to have the password in it. Okay, so this has been a quick review of the 8 vulnerabilities found in the Brothers Inc. printers and some other manufacturers as well. Yeah, you can check out this blog. It has some stats on the CVEs and how many devices were affected, and the impact and technical analysis, things like that. You can also download the white paper and check out the code on GitHub. I'm assuming this will probably be added to Metasploit if it hasn't already. I couldn't see it in there, and maybe this will be used in some CTF as well. I don't know how easy it is to get like a virtual printer device from one of these makes and models, but I would be surprised if it doesn't show up in some Hack the Box machine if it hasn't already. If it hasn't, then maybe you can go and try to make it yourself. And let me know what you thought of this video. I might do some more like vulnerability CVE analysis videos in future. There was another one by Rapid7 on the Lorex cameras, which was a crazy chain of vulnerabilities. Anyway, I hope you've enjoyed this video. If you have any questions or comments, as ever, leave them down below. Thanks.